Hello, this is Amy Brown, Director of Events and Education for Trade Press Media Group, and thank you for joining us for today's webcast, Arc Flash Mitigation, Designing for Safety. Our presenter today is Tony Parsons. Tony is an electrical engineer for Schneider Electric with 20 years experience. He has an emphasis in the areas of computer modeling of power systems, relaying and system projection, power quality and harmonics, and electrical safety. He has authored numerous technical papers on various power systems, engineering topics, and has developed extensive training materials for both Schneider Electric's employees and clients. Tony is currently the representative for Schneider Electric on the IEEE P1584 Arc Flash Hazards Calculation Working Group and is a registered professional engineer in the state of Texas. Today's webcast, our learning objectives include identifying key system parameters that influence arc flash incidents' energy calculations, determine how equipment construction can affect calculated arc flash levels, identify 4 arc flash solution categories: prevention, avoidance, reduction, and containment, and apply a systematic approach to evaluating a system and developing an arc flash mitigation strategy. Before we get started with today's webcast, I'd like to cover a few details about the event. A live question and answer session will follow today's presentation. To submit questions, please use the Q&A panel on the right-hand side of your screen, and make sure to send your questions to all panelists. Our presenter will answer as many questions as time permits. Today's event will also include an interactive multi-choice polling question. We ask that you participate in this poll, as your input is very much appreciated. At the conclusion of today's webcast, you'll receive a PDF of the slides used today. You'll also receive a link to a brief online assessment, and upon successful completion of this assessment, you'll earn your CEU certificate. Today's webcast will also be archived on facilitiesnet.com/webcast. And with that, I'll turn it over to you, Tony.
All right. Well, thank you, Amy. Good afternoon to everyone out there, or good morning maybe for some of you. It's good to have the opportunity to spend a little time with you today talking about arc flash safety. And my plan is that we'll spend this time looking at it from maybe a little bit different perspective than we do sometimes. I don't intend to do a deep dive into looking at the pros and cons of a specific solution, even though we are going to mention some of the solutions that are out there for for helping deal with arc flash problems in a facility. Instead, what we're going to do is back up a little bit and sort of take a high-level overview and talk about some ways to develop a strategy for dealing with the problem. Maybe you've had an arc flash study done in your facility. You've identified some places where incident energy levels may be a little bit higher than you prefer. You're trying to figure out what to do with those. We've developed the material in this presentation based on really years of discussions with different clients and different types of facilities, whether it's commercial buildings, petrochemical facilities, even utility systems. We've used some of the ideas that I'm going to share with you in discussions with some utility providers here in Texas, and hopefully it'll help you make sense of some of the things that are out there, some of the ways that you can actually approach this problem, because it can be a challenge. This is not the easiest thing in the world to figure out how to deal with in an efficient way. Before we get into the details, I want to just very quickly do a little bit of review, just to make sure we kind of start things on a level playing field. What is arc flash? I'm sure most of you have heard these things, but arc flash, NFPA 70E, the standard for electrical safety in the workplace, gives us a definition. It says an arc flash hazard is a source of possible injury or damage to health that's associated with a release of energy caused by an electric arc. So basically what we're talking about are situations where we have short circuits in power systems that flow through the air rather than on the normal conductive path. A lot of times when we look at short circuit currents, you do your short circuit study in order to pick the ratings of your switchgear or panel boards or whatever. What we're assuming is what's sometimes called a bolted fault, the maximum available short circuit current at any given point in the system. When we deal with an arc flash event, we have that fault current now, instead of flowing on the bus bars, instead of flowing on the cables, it's flowing through the air, ionized air, and that changes things quite a bit. The arc itself has an impedance, high level of current flowing through it, maybe tens of thousands of amps in some cases. We're delivering a whole lot of power essentially to a load. even on a low voltage system, you can be delivering several megawatts worth of power to that load, to that arc flash event, and there's enough energy released as a result of that to cause pretty significant release of light, heat, pressure, and sound as a result of that that event. Heat is what we think about probably the most with these events. Look at incident energy levels in calories per centimeter squared and figure out what type of arc-rated PPE to wear. But the other things can be real hazards as well. Certainly there can be enough energy there to cause significant damage to equipment and injury for workers who are unfortunate enough to be caught up in one of these events. So we need to do something about it, right? And one of the things that we can do, or at least one of the places that we can start, is to try to do some kind of assessment to see how bad things really are, right? We do an arc flash analysis. And I think a lot of people have the idea that this is something that's relatively new. I mean, maybe the last 10 years or 10 plus or minus that people have been doing the arc flash studies. We haven't really had ways to do that before. Not necessarily true. We're not going to go into the details here, but some on the slide, some documentation from actually the one of the first methods that was proposed to allow folks to try to actually do some calculations to assess arc flash hazard levels. The idea of doing calculations for this kind of thing dates back to the early 1980s. More recently, what has happened is that there's been extensive work done to test arc flash test to determine arc flash potential in power systems based on typical test setups in lab facilities. Again, I'm going to kind of speed through some of the details here, but basically, if we set up enclosures that kind of approximate a typical piece of power distribution equipment, set that up or hook it up to a source where you can control the voltage, control the amount of fault current that's available, and then those round the round disc in front of the enclosure there are calorimeters. They measure the heat rise produced by the arc flash event. You do that a few hundred or a few thousand times, and before long, you've got a pretty good calculation model that you can put together. And this is exactly what was done in IEEE Standard 1584, the IEEE Guide for Arc Flash Hazard Calculations. Just to give you an idea of what some of the equations look like, here's a sampling from the latest version of that standard. IEEE Standard 1584 published in 2018. A set of equations there on the top that allow you to calculate the arcing fault current level based on your maximum fault current that you calculate with your short circuit study, and then based on the clearing time of the circuit breaker, fuse, or relay in the system, you can plug in a few other factors. You can plug those into those equations on the bottom and actually calculate the incident energy, the amount of heat that the worker is going to be exposed to. So some key takeaways from the calculations. Arc flash incident energy, we'll talk about that in several places through this presentation. What we're looking at there is the heat energy available at a worker's face and chest, measured in units of calories per centimeter squared. That's the typical unit that clothing is rated in, typical unit that the calculations are performed in as well. The arc flash incident energy levels are going to be based on four primary parameters. They're going to be based on the voltage and current that are available there in the system. And with current, we mean the short circuit current at the given piece of equipment that you're looking at. Of course, voltage times current equals power. Power times time equals energy. So we go to the third thing, the arcing duration. How long does the fault actually last before the breaker opens, the fuse clears, or whatever happens to make the arc go away? And then finally, the last thing in the equation is working distance, the last primary quantity. The farther you move away from the arc, the less energy you're exposed to. It's simply common sense, and that can be a very powerful mitigation method, as we'll talk about in a little bit more detail as we get into looking at some of those solutions. The voltage, current, duration, and distance kind of give us those incident energy levels. Out of those four things, current and time really are probably the two most important parts of the calculation. Not that voltage is not important, but voltage, what we're looking at there is typical system voltage, if you're dealing with a power system that's operating at 480 volts, well, I mean, your voltage is 480. That you're going to use that nominal value. That's kind of fixed, but fault current may vary depending on the size of the transformer feeding a portion of the facility, how much cable impedance is in place in between you and the source, even the size or capacity of the utility that's serving the facility. So current, and then time is the other one. Again, we've already mentioned that the longer, the energy is calculated based on the power times the time. The longer the longer that fault lasts, the more energy is going to be delivered to the equipment or to the worker who's standing around. So fundamentally, when we're talking about arc flash mitigation, in many cases we're looking at ways to either decrease the amount of time that the fault stays on the system or increase the distance between the worker and that fault source. It's kind of the original social distancing there, right? If we can move the worker away from the source of the arc, you decrease the amount of energy they're exposed to and reduce the risk as a result. Is it possible to mitigate by changing the current? Maybe. There can actually be some side effects from that. We've had discussions with folks that said, oh, well, we have high arc flash levels. I want to reduce my incident energy levels. Let's put in a current limiting reactor or something like that. Well, when we do that, you run the risk actually of increasing the time that it takes for your protected device to respond. As the lower fault current may mean that it takes longer for a device to operate. We may go from the instantaneous region of a breaker to the short time region, for example. So you have to be careful. You're looking at these mitigation means. Sometimes you change one thing and affect other things in ways that you don't necessarily anticipate. And so we have to be careful when we kind of try to start figuring out how we're going to deal with the problems. Well, just a couple of things on application of the calculations. Again, I think some of you are probably familiar with these kind of levels, but if you haven't seen this, some key incident energy values. 1.2 calories per centimeter squared is what they tell us is the threshold for second-degree burn injury. All these things are measured in percentage. You have a certain percentage of receiving second-degree burn on exposed skin if you're exposed to at least 1.2 calories worth of energy. NFPA 70E, again, the NFPA electrical safety standard, says that you're supposed to wear arc-rated clothing if you're potentially exposed to energy levels greater than 1.2. If you look at those PPE levels, you get up somewhere around 8 to 12 calories. That really is what I'll characterize as a boundary line between low and high rated PPE. And what I mean by that, the 8 to 12, you can probably get by with a coverall that's relatively comfortable, or even treated shirts and pants that kind of give you protection to that level. You get up to the higher levels, the 30 calories, 40 calories, things up in that range. You're talking about wearing, dedicated flash suits with hoods, and rather than just face shields, quite a bit more intrusive, if you will, in terms of the protection that's required. 40 calories per centimeter squared is another magic number that's thrown out there sometimes. A lot of organizations, Schneider Electric included, look at this as sort of the maximum allowable. We won't allow our folks to be exposed to energy levels above 40 calories per centimeter squared. So, that's a lot more than 1.2. Do we really get there in real systems? It's certainly possible. Typical incident energy levels, what I've got here, some calculation parameters, 25,000 amps fault current available, so kind of middle-of-the-road calculation, 40-volt system. So it's low voltage, but it's not, this is not your 120 that is at the wall outlet. 18-inch working distance, kind of an arm's length distance, which is typical for these kind of calculations. If your breaker trips instantaneously, even with those parameters, you're above the 1.2 calories per centimeter squared, 50 milliseconds, typical instantaneous operating time for a circuit breaker. So we're already into the level where we got to take, we have some concerns to deal with. Short time, what if we're not tripping in instantaneous? We're kind of up at the next category. 0.3 seconds or 300 milliseconds, that's kind of middle of the road for a short time delay. We may be kind of pushing the capability of that, kind of our standard PPE, having to get up into the more heavy-duty stuff, if you will. In IEEE 1584, there is guidance that in most cases you're okay cutting off calculations at 2 seconds. The idea being that by 2 seconds somebody has, hopefully your reactions kick in. You kind of remove yourself from the source of the heat, or in worst cases, a worker might be kind of blown backwards away from kind of the most intense arc flash if one was to occur. But 2 seconds, which might apply at your surface entrance equipment, even with those parameters, 25,000 amps, relatively moderate, you're looking at close to 100 calories per centimeter squared. So quite a bit of energy that can be out there available on a real system. So what do we do about it? We typical energy levels can cause injury. What's the solution? Personal protective equipment certainly is part of it, including the arc-rated clothing. NFPA 70E, I already mentioned that. Again, the NFPA standard for electrical safety in the workplace. OSHA also has some requirements that define some of the safe work practices. For OSHA in general industry, it's not a lot of detail behind it. I'll talk in a minute about when we look at some of the details in 70E, talk about a little bit about what OSHA has for utility transmission and distribution systems. They actually go into a little bit more detail for those. Even the National Electrical Code has some installation standards that touch on arc flash protection to some extent. Just real quickly, arc-rated PPE examples, you can see here why I'm kind of making the distinction between the quote-unquote light-duty and heavy-duty PPE on the left-hand side. 8 calorie per centimeter squared rating. So, again, the worker's there in a face shield. He's got a treated shirt and pants to achieve that rating. On the right-hand side, where you want a little bit more protection, 40 calories per centimeter squared. Again, the flash, the full flash suit with the hood, with the specially designed face shield, and you can just see quite a bit a higher level of protection that's required when we move up in those energy levels. I mentioned the National Electrical Code. One of the things that has changed in recent years, and that is still kind of rolling out as different states, different local authorities adopt new additions of the code at sort of different rates, is requirements, or the requirements there for arc energy reduction. This one here talks about NEC 240.87. There is a similar article for NEC 240.67 that deals with fuses, but I'm just showing you one to kind of give you the idea. But 240.87, and this text here is based on the 2017 National Electrical Code. The 2020 is essentially the same. There's a little bit of a change, but it still hasn't been adopted in most states yet. So I think 2017 is still fair to look at. But it basically says if a breaker is rated or can be adjusted to 1,200 amps or higher, you have to apply some method to reduce clearing time, either zone selective interlocking, differential relaying, a maintenance switch, energy reducing maintenance switch with a local status indicator, an energy reducing active arc flash mitigation system, an instantaneous trip or instantaneous override that's set less than the available arcing current, or an approved equivalent means. So certainly, lots of options there. But the point being, these larger circuits where maybe more energy available, we are required now by the code to put in some means to help reduce the energy levels. Finally, NFPA 70E requirements. Again, the safe work practices. My summary, but very high-level summary. But de-energize equipment before you work on it. And if we only did that, life would be very much more simple. But NFPA 70E, makes some exceptions for some common tasks, including testing and troubleshooting. Even going through the lockout tagout process to de-energize equipment can potentially expose workers to arc flash hazards, because one of the things that you're supposed to do during the lockout tagout process is test to verify that voltage has been removed. And so there's even potential exposure there. NFPA 70E goes on further to define requirements for risk assessments. And again, here's kind of my summary of what you need to do with these arc flash risk assessments. Well, my take on it is that you answer three questions. Number one, are workers going to be exposed to a hazard? Just because you're, you are around electrical equipment doesn't necessarily mean that you're exposed. Generally, to be exposed to an arc flash hazard, you have to be interacting with the equipment kind of in a more direct manner. Pulling covers off certainly would do that. But if you're doing some kind of task, whether it's testing or whatever that may expose you to a hazard, the next step would be to figure out how severe that hazard might actually be. So maybe that's where you get involved in performing an arc flash study. And then finally, the third item, what mitigation means would you take in order to reduce the risk to the worker? I mentioned, and I don't have it shown here on the slide, but I mentioned OSHA requirements for utility transmission and distribution systems. Just to kind of mention those for completeness. OSHA 1910.269 was revised a few years back. It's 2015 or 2016. I don't remember exactly which one now, but the specifics in the requirements are a little bit different than what are contained in NFPA 70E. Which would apply mostly to kind of the commercial or industrial facilities, but I think in a lot of ways they're very similar. Some of even if the details don't line up exactly, OSHA gives the idea that if a worker is going to be exposed to hazardous energy, you need to go through the process of performing a risk assessment. You need to go through the process of estimating the incident energy to figure out how bad the exposure would actually be, and then it talks again about how providing appropriate protection and mitigation means to those workers in order to reduce the risk. So again, regardless of what kind of system you're dealing with, we've got some of the same concerns and same things that we look at to try to deal with the problem. NFPA 70E gives us another thing that can be useful. It gives us a mitigation hierarchy. Talks about different mitigation techniques ranked from the most to least effective, and starting right up there at the top, elimination. If we can eliminate a hazard, hey, we don't have to worry about it anymore. And I've got a thing over there that says, not practical in many cases. Lockout tagout is not elimination. Certainly you can't eliminate electricity from a facility if you have electrical loads. I mean, we can't get around that. The last part will get some debate. The reason, a lot of people do look at lockout tagout and say, well, this is at least temporary elimination of the hazard. And I understand that. If you place a system in an electrically safe work condition, then, you're at a zero energy state. You can go work on that, and it's the way to do it. I've just seen too many cases over the years where I've seen, I guess reports of incidents or investigations that showed that people did the lockout tagout improperly. And so, yes, we're eliminating the hazard, but again, there's the potential for exposure as we do that. It would be nice, even if we're going to de-energize equipment to work on it, to try to deal with hazards at another level. Kind of the other end of the spectrum, down there at the bottom, personal protective equipment. A lot of people think, okay, this is what we need to do first is get workers in the proper PPE, and then everything else will fall into place. But really, this is supposed to be the last line of defense. We should do things before we get there. I've got the third one highlighted, engineering controls. My term or my explanation of that would be product or design techniques that can be used to hopefully engineer the hazard out of the system. That's really our focus in this presentation, is looking at the details of some of those things. Where do we apply those engineering controls? Maybe service entrance equipment or any equipment fed directly by a transformer. The problem there might be a slow response of a primary protective device, so the energy levels can get up to those certainly well above 1.2 calories, in some cases maybe even above the 40-calorie level, and that tell us that we need to do something about what we're looking at there. Similar problems can appear on any larger circuits, especially those downstream of fusible distribution. But to be fair, you can have problems downstream of large circuit breakers as well, depending on how they are set up and configured. That's one of the reasons that the NEC has those requirements in for breakers and fuses 1,200 amps or larger. There may be large amounts of fault current required for fast operation of those devices, and it can result in high energy exposure that way. Other problem areas, and we'll talk about this a little bit more when we get to looking at our strategies, but maybe a problem area is not where energy is the highest, but maybe it's where exposure is more frequent. such as MCC buckets or control panels. You know, we might have very high energy levels at the service entrance equipment, but realistically, on a day-to-day basis, electricians are not getting into that equipment. You know, it's just something they don't interact with very much, but they're having to get inside control panels or MCC buckets almost on a daily basis to troubleshoot or reset something. You know, maybe we need to look at those as well. And again, we'll kind of develop that in a little bit more detail as we continue through this. One example, problem area that will let me highlight one more thing before we get into the solution categories. I've got a simple system here, utility source on the left-hand side, a 1500 kVA transformer, giving service to a service entrance switchboard down there at the bottom at 480 volts. And I've just kind of run the numbers there. Instant energy, 78.57 calories per centimeter squared. It's almost 80 calories per centimeter squared there at the service entrance. And why is that? Because I've got my protection there is the fuse on the primary side of the transformer. That FCT there at the bottom, the fault clearing time, 2 seconds. How do we get there? You know, you look over on the right-hand side, I've got 11.68 KA, 11,680 amps of arcing fault current. If I have an arc flash event there at that switchboard, you follow the arrow up, the red arrow up to the fuse curve, and they intersect beyond 2 seconds. We cut calculations off at 2 seconds to get the 78 calories. Okay, that's high. I already told you service entrance equipment would be a potential problem, so why am I showing you this? One thing, you may have noticed I've got a main breaker in this switchboard over here on the left, the 2,000 amp main. Over on the right, this light blue curve, that's the curve of the fuse, the utility fuse, but then I've got the circuit breaker there as well. But how come I ignored that? Why did I go up and look at the fuse instead of stopping there at the circuit breaker at 0.2 seconds rather than going to 2 seconds, whatever it would be? Well, that's where one of the learning objectives we talked about was looking at how equipment construction might affect arc flash levels. Just one more slide to show you before we get into solutions, I promise. But a potential issue that we need to consider when we look at these things, zones of protection. And I've got what's probably about the simplest thing here on the right, just a low voltage panel board. And I've got a couple of zones shown here. Zone 1, the line side of the main protected device, so maybe those main lugs right there at the top of the breaker. We don't have cables coming in on this one, just to simplify it a little bit. But if I'm maybe my energy is a little bit higher there than for Zone 2, the load side of the main device. Typically, that would be the case. Zone 1 would typically be higher because in a power system, we want coordination between breakers. That means that stuff that's further up toward the source takes a longer time to clear the fault. So Zone 1 typically higher energy than Zone 2. But if I'm doing something in that panel, I want to test for voltage in that panel, I pull the cover off. Note that I'm exposed to both Zone 1 and Zone 2. I don't really have any kind of meaningful separation in there. There's nothing that isolates me from Zone 1 as soon as I pull that panel cover off. So I have to protect myself for whatever the worst case exposure was going to be. Simple enough with a low voltage panel board. What about other equipment? It's something we need to consider, and I'm not going to go through every potential scenario and tell you that for this you do this, for that you do that. But just think switchboards, low voltage switchboards. I mean, they may not. They're obviously bigger. They don't hang on the wall like a panel board. They're freestanding on the floor. But one of the things that they would share in common is that there's not a lot of isolation between sections or between compartments in a low voltage switchboard. Low voltage switch gear or medium voltage switch gear, which does have breaker cubicles and isolated compartments, maybe things are different. The point being, these are, it's an example of something that should be considered when we're looking at doing arc flash hazard calculations. Equipment construction is really one of the variables out there that ought to be looked at. Okay, so we've kind of set up the problem. Let's start, talking about what we're going to do about it. And I want to look now at solution categories. Talk a little bit about some of the individual solutions as we go, but my contention is that pretty much any solution out there can be lumped into one of four main categories. I think it's important to understand that because those categories share some characteristics. First one we're going to talk about is reduction solutions. I want to talk to you about what they do, first of all, what it is, but what those solutions do, and maybe more importantly, almost in some cases, what they don't do. We need to understand if we're looking at any given solution, what it does for us and where it still leaves some gaps in the protection. Reduction solutions, the first one, I start with that because these are probably the most common, probably things that people think of first in many cases, but these are just solutions that are intended to clear the arcs quickly to reduce the available incident energy level. And as we talked earlier, incident energy is proportional to time. You clear the fault more quickly through using things like fast-acting fuses, circuit breakers, or relays. We can reduce those energy levels. Sometimes we can't do that without messing up the selective coordination that we like to have in a system. So we do things like put maintenance switches on the breakers or relays so that we only have to have this coordination for a short period of time. You turn the maintenance switch on, settings are reduced, worker is protected. When the work is done, you turn the maintenance mode back to off. So you kind of restore normal selective coordination. Energy level goes up, but you're not as concerned at that point because there's no one there actively working on the system anymore. The third thing I've got there, what I call arc flash relaying. We've seen this developed in the last, particularly over the last decade or so, more and more systems that really are kind of dedicated towards arc flash detection. One of the big things, big categories of that type of solution are optical systems, fiber optic or point sensors that actually look for the light that's created by an arc flash event. You can see in the picture on the bottom right there, some pretty bright light that's associated with that arc flash and that equipment. And so if we can detect that, there are those relays out there available that can clear or can operate very quickly, as little as 2 milliseconds or less when an arc flash event is detected compared to, typical detection times that are at least 10 times longer than that, and that's for things that are operating very quickly. So it can be a very powerful solution method in order to help reduce those arc flash energy levels. There are some cases when they may not provide a tremendous benefit over other things that you can do. There are some cases where if you're trying to meet a certain goal, that's the only way that you can get there is to put in optical systems. So again, we'll talk about kind of defining what your goals are and looking at your different solutions that way as a result. But certainly a powerful tool in the toolbox. But sometimes you don't even have to get that fancy. Sometimes it may be as simple as the fourth thing I've got on the list: optimizing settings of your existing devices. I am amazed on a fairly regular basis how many times I look at studies that have been done by my colleagues, by others who simply have missed the opportunity to set up the devices, the protected devices in a way to really minimize those arc flash levels. And in some cases, I've seen folks that just really didn't understand the full capability of the relays that they might be working with. Other cases, it just was something that was not considered as you went through with your coordination study. Certainly something to look at there. One thing to note, the last bullet point down there in the bottom, I said these solutions don't affect the likelihood, but they do reduce the severity. When we talk about arc flash hazards, there's really kind of two components to it, risk and severity. Risk, the likelihood of an event occurring really is looking more at the probability, aspect of it. How likely are we to actually create an arc flash when we're doing whatever it is on this equipment? The other side of the coin, though, the severity. If we put a maintenance switch in a piece of equipment, we may not reduce the likelihood. We may not make it more or less likely to actually create an arc flash if we're going to go in there and do some voltage testing, for example. But the goal of these generally would be to reduce the severity. If an arc does happen, let's clear it more quickly and reduce the level of energy that the worker is going to be exposed to. The next category of solutions treats things a little bit differently. The next one is containment. Basically with this, when I'm talking about are solutions that are designed to contain or redirect the arcing fault and its byproducts, what I'm talking about here really arc-resistant switchgear. The idea with the arc-resistant switchgear is that even if an arc occurs inside of it, you protect the worker who's standing adjacent to the equipment. Now they may still be scared when the explosion happens inside, but at least their clothing ideally is not going to be caught on fire. They're not going to wind up in the hospital with the burn injuries. In a way, you can think of kind of the PPE sort of being built into the equipment. There may be heavier gauge steel. As you can see on the bottom, the hot gases and flames and stuff kind of shooting out the top. In a lot of these systems, you have some kind of ducting on top of it to take those and vent those away from the vicinity of the gear itself. Take those out to somewhere where nobody is standing. and provide some significant protection that way. Certain industries, use the arc-resistant switchgear on a pretty extensive basis, oil and gas, utility segment. Others, not as much, but again, it does some nice things for you. But it doesn't solve every problem that you have. One of the things it doesn't do is provide benefit for intentional exposures. What's an intentional exposure? Well, think of the cases where, for example, you're doing lockout tagout. You want to test to make sure voltage has been removed from this gear. What do you have to do in order to do that? You have to open a door or remove a cover on the equipment. Well, as soon as you do that, the arc-resistant switchgear is not arc-resistant any longer. So we've kind of bypassed the protection. If you want to use this, you really need to think about what kind of work tasks you're trying to protect your workers from and make sure that those are compatible with the ratings and the intended operation of that gear. Third one, avoidance solutions that remove the worker from the vicinity of the hazard. We talked about how working distance affects the calculation. It's a little bit of an approximation, but energy falls off roughly as 1 over distance squared as you move away from the source of the arc. So if we can do certain tasks remotely, remote operation of breakers, remote racking of withdrawable circuit breakers or contactors, we can do those, even do those outside the arc flash boundary where the energy will be less than 1.2 calories. We have done a lot to protect the worker. And so, again, several examples of this: remote operation, remote racking, infrared windows or embedded thermal sensors. I got the infrared windows kind of shown up there on the top right, so you can do your thermographic scanning without having to remove covers on energized equipment. Kind of the newest trend in this area would be those embedded thermal sensors, wireless sensors that you can put inside the equipment to get the same data out on a continuous basis. You're not opening the covers, you're not exposing someone to the hazardous energy, and so we can reduce both the likelihood and the severity to the worker. One consideration, and we'll come back to this later, hazard level will be unaffected at the equipment itself. You're trying to protect your equipment from potential damage. This may not be the way to go. The last one, prevention solutions intended to make arcing faults less likely to occur to begin with, because the easiest arc to manage is the one that never happens. So how do we do this? Additional barriers and compartmentalization inside of equipment. You're starting to see equipment with features like that are shown in the top couple of pictures. Shields in breaker cradles or on the finger clusters in the back of the breakers make it less likely that you start an arc when you're racking the breaker back into itself, for example. On the bottom left is an example of insulated bus, solid insulated medium voltage switchgear, where theoretically you can go and touch that when it's energized and you're not contacting any energized parts. Certainly, obviously, reducing the risk that way. Just other equipment construction. On the right hand side was a picture I took in a VFD cabinet that a customer had built up, where just some encapsulation of incoming conductors, the barriers around the individual fuses, and the idea being that this was kind of like our zone 1 that I showed you in the panel board a while ago. You put some barriers around that zone 1, and then anything downstream of that, you've got some added protection. I think in the long term, we're going to see more and more equipment that's built with these kind of prevention solutions in place, trying to engineer the arc flash hazards out of the equipment overall. We're not quite there yet as an industry, but I'm encouraged by some of the things that I've seen in recent years where we're kind of starting to move that way. So we've got our solutions. What do we do with them? Really, the keys to kind of the designing for safety, developing a strategy. What we've done here is put together 5 questions that we've used again in real facilities, helping us sort through the different options that are available and trying to get to getting to the idea of building a strategy to deal with arc flash mitigation. Question number 1, probably the most important one: what does safety mean to you? The idea here is that in a lot of cases, at least what I've found, is when we're dealing with customers, they've had the study, the arc flash analysis done in their facility. They want to do something about it. What can we do? This is usually this will be the place that I'll start. Okay, what are you actually trying to accomplish? And in a lot of cases, some cases they have thought about it. In many cases they have not. If we're going to mitigate, though, I think it's important to really look at what the end goal actually is. do we just want to get a system where we meet all the code requirements? We can do that. You know, I showed you the list of things that were called out in NEC 240.87. You can pick whichever one of those seems to be the most appropriate and move on. What if we say we want to have, you know, kind of a performance level set around incident energy levels? Where, you know, code requirements, yes, we want to comply with the code, but we also want to make sure that we meet certain levels of incident energy in our facility. I want no more than 40 calories anywhere in my location. Okay, I can find you a set of solutions that will help you do that. Other folks say, I don't want anything more than 8 calories. Well, that may require a different set of solutions. Some that we've worked with say, I want my arc flash incident energy as low as possible throughout the facility. You know, what may get you below 40 calories may not get you below 1.2 if that's what you're shooting for. Point being, whatever the goal, you know, you can work towards getting there, but you need to define what those goals are. Goals drive solutions, and the optimal solution for each one of those criteria that we talked about may be different. I don't think you can solve the problem if you really haven't defined where you want to go, if you haven't defined success. And so, again, the first step, define a set of safety-related performance requirements. The second one, look at where the exposure is. We've talked about this a little bit already, but, you know, how do you prioritize mitigation actions and make the best use of a finite budget, which, you know, we know they always are, right? One of the common answers, start with the highest incident energy level and work your way down. We talked already a little bit about, you know, what if your workers, though, are into MCCs or control panels on a regular basis, having to do troubleshooting or whatever, even if the incident energy levels are lower, their exposure is higher, and it may make sense to look at solutions for those locations first, rather than, you know, simply starting with the high energy locations where you don't have much interaction. So again, a little bit different consideration than we look at times. Question number 3, how will you evaluate likelihood versus severity? And this gets back to what we were talking about earlier with kind of the two aspects of safety, you know, the probability versus kind of that level of hazard. In a lot of cases, what we find is that if we look at a solution, a potential solution, if you can't reduce the incident energy level, if you can't reduce that calorie per centimeter squared value that's shown on the arc flash label, people lose interest in it, right? That means like remote racking. That would be one where, you know, if you're worried about protecting people from potential hazards that exist when you're inserting a withdrawable breaker back into the switchgear, remote racking is certainly a good way to go and do that. It doesn't change the arc flash calculation. It doesn't change the value on the incident energy level. That shouldn't mean that it's a solution that just gets ignored, but realistically, that's what happens at times. So how will you evaluate likelihood versus severity? And in some cases, when is it okay to forget about bringing the numbers down and looking at other solutions? Question number 4, what about equipment survivability? This one gets a little bit tricky. You know, we get asked sometimes at Schneider Electric, you know, hey, I want to bring incident energy levels down to help protect against equipment damage. How low do I need to get it to get those incident energy levels to be before I can be assured that I can re-energize my equipment after it has an arc flash? We don't know. I mean, we haven't tested to really figure out what that threshold is. Now, common sense would tell you it's a lot easier to recover from a 4 calorie per centimeter squared event than it is from a 40 calorie event. And this may be one of the considerations. We've had discussions with some folks that are operating critical facilities, you know, data centers, hospitals, where, you know, this has been part of the consideration in bringing incident energy levels down at certain equipment. I would just say, you know, certainly it's not a bad idea, but nobody wants equipment damage, right? But you got to be a little bit careful about applying this as one of your criteria. If you do and you stick to this strictly, then you might wind up throwing out certain things like arc flash maintenance switches that, you know, are only active part of the time, so you really may not be able to count on them all the time to help reduce equipment damage. But they, you know, for personnel safety, they may be perfectly wonderful solutions that you can apply. Certainly, equipment survivability, something to think about, may not be the thing that you can use to drive the bus, so to speak, in all cases, because it kind of moves your solutions in a certain way. Last question, kind of a catch-all. What are the limiting factors? Maybe budget. You know, you like putting this kind of thing in or that kind of thing in, but but realistically, what can we do to, within the amount of dollars that we had to work with, what can you do with the available footprint, particularly in retrofit solutions? I like arc-resistant gear, but arc-resistant gear may be a little bit bigger, or may require a larger ceiling height because I got to get these ducts or plenums put in on top of the equipment. Maybe I can't fit this in the same space that my conventional switchgear is now. How much downtime is it required to install a retrofit solution? You may have to think about that. What about effects on reliability? We hear concerns sometimes with maintenance switches. What if my electrician forgets to turn it back off when he's done? Will that impact selective coordination? It probably will, and something that needs to be thought about. Equipment maintainability can even be an example. You install a state-of-the-art optical detection system and high-speed shorting switch. What kind of maintenance or testing program is required to make sure it operates as it's designed and intended? If you have to test it every 2 years and you're in a facility where you only have maintenance shutdowns every 4 years, something you ought to think about at least before you kind of move down that path. And I'm closing in on the end here. Just a couple of general recommendations. Perform a study. You don't know where to mitigate until you do some calculations. Even preliminary results can help guide the final solution. We have discussions sometimes with folks that, we're still in the design stages. We don't know what the final numbers are going to be. Don't wait until everything's built and then run the calculations and then figure out where your hotspots are, because it's so much harder to get solutions put in as retrofit than it is to get them, when you first build the facility. Consider equipment construction and zones of protection. We already talked about that. Validate with calculations to confirm the results before you put the solutions in. Service entrance gear is always a problem because you don't have control over the utility. So maybe separate or isolated mains can be something you look at. Remember, lower mitigation targets require ever faster tripping. And so that means, if you're really trying to get aggressive and trying to get down to 1.2 calories or less than 2 calories or whatever, either you're going to have to compromise on selective coordination, or you're going to have to look at more and more expensive mitigation systems in order to get down to those levels. And then last but not least, don't forget that there are solutions other than a reduction of incident energy, and don't rely on personal protective equipment as the only solution. The quote here from NFPA 70E, while PPE requirements for this section are intended to protect the person from arc flash and shock hazards, and then it goes on to say, even if you wear the stuff that it recommends in NFPA 70E, there is the possibility that you may sustain some kind of burn injury. But I've got the highlighted section there. Even if that happens, burn injury should be reduced and survivable. Okay, that's good. A survivable injury is better than the other kind. But I know if it was me, if I'm going out to an electrical, to an industrial facility, working around electrical equipment, if something happens, I would like to do better than just sustain a survivable injury. If we keep in mind the solutions that we have, keep in mind these strategies to try to implement those and look for optimal ways to mitigate arc flash levels in a facility, I think we can get there. And with that, I am done with my presentation. Amy, send it back to you. We got, I think, a couple of polling questions, and then we'll get into some time for a question and answer from the audience.
Wonderful. Thank you very much for the presentation, Tony. And yes, it's time for our polling questions. We have 2 questions today. The first question is, what would you like to learn in our next webinar? The options are A, safety practices, B, modernization solutions, C, analytics and technology, and D, new products coming to market. And the second question is, would you like a representative from Schneider Electric to reach out to you regarding your facility's safety? A, yes, B, no. Again, thank you very much for using the panel on the right-hand side of your screen to answer these polling questions. In a second. Thank you very much for participating in the polling question. And now we'll continue on to the Q&A portion of the presentation. Just a reminder, you can submit your questions for Tony on the right-hand side of the screen. And we'll go to our first question, Tony. The threshold for second-degree burns is 1.2 calories per square cm. Why wouldn't that be the goal for every system?
Well, it would be a good goal to meet, but the challenge is that 1.2 calorie per centimeter squared, particularly if you have if you've got a system with a lot of available energy, or a lot of available fault current, just a large system, it can be very difficult to reach that level. I mean, it's a pretty low threshold. Even with circuit breakers tripping instantaneously, if you have larger fuses, there's kind of you sort of reach almost a finite time where they're not going to trip any more quickly, and it just becomes difficult to have protective devices operate quickly enough to get you down below that 1.2 calorie level. For smaller circuits and smaller, it kind of depends on kind of the makeup of your system, maybe even your voltage level to define exactly what smaller is. But smaller circuits, in a lot of cases, we can get there. It's just, it's a good goal. It's just one that you're not going to realistically be able to make in all situations.
Great. The next question, are the arc flash mitigation solutions you talked about available for retrofit or only for new equipment installations?
Okay. Most of them would be available for either one. You can certainly the relaying that we talked, the protective relays that we talked about, they can be ordered in new equipment. They can be used as upgrades for existing, like electromechanical relays, for example, that may have been out there for a number of decades in some cases. Probably the only exception would be arc-resistant equipment. I'm not aware of anybody that's come up with a way to take standard equipment and kind of put on a retrofit kit to upgrade that to be arc-resistant according to the IEEE standards. But other than that, you can do it either way. Now, the retrofit solutions sometimes are more difficult. In most cases, when you put in one of those solutions, it will require some downtime of your system in order to get those installed. So it can be a challenge, but it is possible.
Great. Thank you. Our next question is, was machine learning process used to calculate the polynomial factors in IEE 1584?
It was more of a as I understand it, more kind of a statistical analysis. There was a professor at one of the universities in Texas that actually kind of led that effort, and he as I understood it, used some sophisticated statistical analysis techniques to do some curve fitting. Machine learning, to me, that means a little bit more kind of artificial intelligence kind of stuff applied to this. I don't think they went that route exactly, but it was certainly, there's certainly some pretty good analysis techniques that they used to get there. And hopefully that's close enough to the answer of what the questioner is looking for there.
Great. One person had a question regarding, on your slide 14, you had equations based on low voltage. Are the equations different for high voltage, or are they the same?
No, they are different. In the criteria of IEEE 1584, low voltage would cover things 600 volts and below. The medium voltage would go from 601 up to 15 kV. And then above 15 kV, really that's outside the scope of IEEE 1584. But yes, the equations are different. There's some similarities, but they are different. The processes are a little bit different. And just note, again, I showed you kind of an example there on that slide of the equations. That doesn't have every factor that you need, obviously, in order to do a calculation. The IEEE 1584-2018 gives us some increased accuracy and resolution in our calculations, but it's at the expense of having some fairly complex equations in there. So we're fortunate that there are a number of companies out there that provide good analysis software that we can use to kind of take some of the calculation burden off of us.
Great. Our next question is, for utilities, how is equipment like load break elbows treated in arc flash calculations? It's not an exposed part, but it can fail.
Yeah, I mean, there are no calculations that really, that I guess would take into account so much the insulation, if you will, around the equipment. I'm familiar with the load break elbows, and the pad mounted switchgear or whatever. If you were doing a calculation on those, kind of what you assume when you're doing an arc flash calculation is that an arc could occur. and you're looking at the potential energy that would be available if the arc were to occur. Now, if you want to look at it from the standpoint of, well, is an arc actually likely to occur when you do a certain task based on the equipment construction, based on, again, what type of insulation is there, that's kind of a different matter. And there, again, that gets into the risk assessment requirements that are in both NFPA 70E and in the OSHA, the OSHA guidelines, where you essentially determine if whatever task it is that you're doing on that specific equipment is likely to cause an arc flash or not. But if you're strictly talking about calculating the incident energy numbers, you kind of start with the assumption that yes, we could have had an arc flash, and let's see how bad it will be.
Great. Next question is, where does the liability rest if an organization does not do this type of study to determine the hazards?
So, I'm not a lawyer. I'm an engineer, so I hate to get into some of the, too much into the liability thing. I would just say that if I was a facility owner and I had workers out there who were, potentially exposed to hazardous energy, I would rest a lot better at night from a liability standpoint, from almost any other standpoint, if I had done the assessments, if I had trained my workers properly, if I had supplied them with the appropriate protective equipment that they needed. And I'll just leave it at that.
Great. Are all mitigation solutions effective for either parallel or series arc flashes? If not, which are applicable for each?
Okay. Now, parallel and series, I think we'll get more into kind of the low voltage, almost residential kind of things. The arc fault circuit breakers that are applied in residential, and there's kind of different algorithms that they may use for parallel or series arcs. When we're talking about arc flash, kind of in this sense that I'm looking at, with the real explosive release of energy, I think what we're looking at more there is, I think it would be parallel arcs by that terminology. But basically, we're talking about arcing from phase to phase or phase to ground that causes a significant release of energy. And it's the other kind of the one that the breakers that you may have in your home, if you've had a home built in the last 10 years or so that have some arcing detection capability, that's more of a low energy type arc that it still releases heat, but it's not the same kind of explosive event that we're looking at here with what I've been talking about today.
Great. The next question is, if someone is interested in putting together an arc flash mitigation work practice strategy, where would they begin, and what would they need to do in terms of budgeting for that kind of strategy?
Okay. Yeah, I mean, I think one of the places to begin is to, well, there's a couple of them. Preludes really to kind of getting out there and mitigating arc flash levels themselves. One of them we mentioned kind of toward the end of the presentation. One of the first places to start is really with doing an analysis. How do you know what to fix until you've kind of quantified what the arc flash levels are in the facility? There's different ways to do arc flash evaluations, but whatever they are, do those, get a handle on the levels that you have in your facility. Second thing, and really even before you get into trying to solve the problems, make sure that workers are trained, that you have a proper electrical safe work practices program in place. You've documented what the workers are expected to do. You've trained them appropriately. You've given them the proper PPE. You start with those two things, and then kind of work from there. As time goes on, you can that study gives you the kind of the basis for ideas of what we need to fix. It can even help you get the information that you need to really start to prioritize things. And but if you don't have the foundations in place, you don't have that analysis done to identify the potential problems, and you don't have the good the safety program and kind of expectations of workers and such in place at your facility, then you really need to get that in place before you start going into more detail.
Great. We've had a few individuals reach out with questions regarding labeling and warning requirements. Can you just touch on some of that, and if the generic labeling is available and practical, or how specific that needs to be? Okay.
Well, the labeling requirements are in NFPA 70E, and it's in Article 130, and I'd forget exact kind of subparts of that, but in Article 130 that has the requirements in NFPA 70E for arc flash labeling. And basically what it says is that if you have equipment that's likely to be inspected, serviced, maintained, et cetera, while it's energized, you're supposed to label it to show the potential arc flash exposure for workers. And there's some of the specifics. It gives some specifics on what has to be on the label, but really the goal is that you provide information that workers would need to know in order to be able to select the proper protective equipment before they open a cover or get into that gear. As far as generic labels, really the intent is that you're kind of assessing equipment on a one-by-one basis. Because you have a low voltage panel board, if there are a lot of different shapes and sizes of panel boards that are available. A panel board that was placed near the service entrance in a facility might have a very different hazard level than one that's just feeding a few lights out in the parking lot or something. There are ways to do that. That analysis to kind of get a handle on where you come in with the potential hazard levels that you're exposed to. But really, I'm not sure if there was a specific question about a generic label. Maybe we can look at that. But in general, it's not supposed to be just a label that says, "Hey, danger, arc flash, and watch out." The intent, at least of NFPA 70E, is to give you a little bit more specific information so that you can be protected against the hazard that you may be exposed to, the level of hazard.
Perfect. Is there some? Excuse me. Can you talk about a scenario or example where you would have a series of arc flashes rather than a parallel arc flash?
What we're talking about with these arc flash events that kind of in the high power systems that I'm talking about. Again, it's where you've had a breakdown in insulation, maybe from phase to ground through either contamination of insulators or in some cases we've seen critters, rats or snakes or whatever, get up into the gear and kind of bridge the gap between phase and ground and maybe create an arc in the process. You can also have breakdown from phase to phase. There have been cases where workers have dropped tools and they've kind of bridged the gap from phase to phase. There have been cases where workers have gotten injured when they're in doing voltage measurements inside a piece of equipment, and maybe they accidentally make contact with exposed portions of their test leads to kind of complete the circuit where normally it wouldn't be completed. And so when I don't usually think of these things in terms of series or parallel. I'm thinking of it in terms of breaking down the insulation from phase to phase or phase to ground. And again, in a power distribution system, certainly 208 volts or higher, you're going to have enough energy there to potentially sustain an arc flash event until either you get lucky and it kind of blows itself out, or until a protective device operates, and that can result in significant energy. So whether you want to characterize those as series or parallel or a series of arcs, there have been cases where arcs have kind of extinguished and then reignited. I think that's a little bit different than what the question was getting at, but a series of arcs rather than a series arc. Either way you cut it, you go phase to phase or phase to ground with this kind of thing, and you're going to cause a potential issue.
Perfect. And I know we're past that hour mark now, but one final question from the audience is, how often should you go back and look at those arc flash studies or reevaluate?
Okay. Yeah, good question. NFPA 70E, again, gives us some guidance on that. It has a section that says that arc flash studies should be updated when there are either major changes to the facility or at least every 5 years. And so major changes, if you've had a facility and you've, for example, added a standby generator to make sure that you can ride through, ice storms or hurricanes or whatever the case may be. If you have equipment now that's fed from generator, the labels that you have on your equipment from when it's fed from utility are no longer valid for that case. It's two different sources. You would need, that would be a great example of one where you need to look at that, or certainly adding equipment, you would need to look at those. The every 5 years thing, we've been in facilities where, every 5 years we kind of go back and revalidate things and really find that not much has changed. And so it may be just kind of a process of looking at the previous results and saying, okay, these are still valid. In other cases, we find that the utility has upgraded their lines, or maybe they've had to change out a transformer because load is growing. They're adding additional process equipment in their facility, and so levels need to get updated. Those are the guidelines in 70E that either when major changes are made or at least reassess it every 5 years.
Great. Thank you again, Tony, for an excellent presentation. I hope our attendees really found some value in the content for today, and we hope you stay safe and stay healthy. Thank you again to Schneider Electric for sponsoring this webcast and for Tony for presenting.
Thank you. Thank you, everyone, for your attention this afternoon.
And just a reminder, you will get a copy of today's slides, so that'll be emailed out to you later today. And then we'll also be archiving this webcast on facilitiesnet.com/webcast.